So okay, so this is the third part of the talk, but you are not, like, I don't expect you to have attended my previous talks, and I'll cover those topics. Like, who did attend Dana Scott's talk 2 days ago? Yeah, so that was an important part, because at least we will know that closure operations, they are like very big things in topologies. Well, in a sense, it is a topology. We'll get there. So I'll be using categories, right? Not all categories, but here are several. Oh my God, rendering. Nice. Let me try to drag it as big as possible. So later maybe. So set is a category of sets, like everybody knows, right? It's not a set of sets. And 2 is a category with 2 objects, which is like one object, another object. They're usually denoted as 0 and 1, and an arrow, and of course 2 identity arrows. That's it. So category 2. Category 3 is like this, but there's one more object. So we have 2 arrows. We'll need one more, right? So that's it. That's all that we need for composition. Now, these are simple things. N is a category of natural numbers. It's like this, but we go forever up there. So it's, again, a partial order, like these 2 are partial orders. What's more important, if you have 2 categories, you can look at the category of all functors from category B to category A, like in this example. So they form a category. Objects are those functors, and natural transformations, whatever they are, they're morphisms in that category. So here are 3 examples. Set to the power of 2. It's not the square of set, because we take functors from this category to set. So that's why it says functors from small categories or from finite categories are also called diagrams. So what does it mean that we have a functor from this category to set, right? This object gives us a set S0. This object gives us another set S1. And this arrow gives us a function. So any pair of sets with a function from the first to another is a functor from this to sets. That's it. So what's, if we have like S0, S1, T0, T1. So what would be a morphism in this category? It will be a pair of these functions like F0, F1, such that the picture commutes. So you can say, oh, it's a category of functions, right, in sets. Yeah, it is. So if we add one more object, so we'll have what? 2, right? So we'll have a function S2. So 2 functions that can be composed. The category of these like pairs of functions that can be composed form a category S to the power of 3. If we take the whole partial order of natural numbers, so we'll have a category of n diagrams, diagrams over natural numbers, meaning we'll have a set 0, arrow set 1, arrow set 2, and so on. If you are familiar with TLA, TLA plus, temporal logic for applications by Leslie Lamport, that's the kind of category that is participating in all those like discussions about the logic. So the question is, what's the logic, right? What's the difference between like a logic in this specific case and a logic in set theory? Let's, okay, let me try to render it again. Present. I hope we'll not have. So suppose we have, instead of those simple diagrams that I showed, suppose we have this kind of diagram, like artistically representing a database schema. So we have a type user, well, it doesn't have to be in a database, it can be like a part of your code, right? A type user, and 3 projections, 3 arrows. Name, which is like gives us a value of type name. email, which gives us a value of type email, and date of birth gives us a value of type DOB. So what if we are trying to introduce some constraints? We can introduce constraints on name, like it could be a good name, a bad name. Bad name may be just like an empty string, or null, it's a bad name. So how about email? Email can be validated, so it's email or not. So like good or bad. Date of birth could be good or bad. So now if we have user, right? So what can go wrong with user? A user can have bad name, then the user is bad. Bad email, then the user is bad. Bad DOB, or like a combination of them. But what can also happen is that name is good, email is good, date of birth is good, the user is bad. Well, I'm not giving like specific examples of LambdaConf, but you probably know what I mean. So this happens, right? Meaning that the combination of 3 bits doesn't fully describe our logic, so it's not Boolean. This logic where like some combinations, well, all those possible combinations is not enough. We cannot have, for instance, like good user with a bad email. Well, like in real life, it happens all the time, but not in this logic. So that's why we have to look further. That's what I was talking about, like last year, maybe the previous year, that the logic that you are dealing with is not always Boolean and more. In real life, we deal with non-Boolean logic more frequently than we can like admit. So that kind of, this is the result of introduction of Aristotelian logic, like in European discourse, like many, many years ago. So we have to liberate ourselves from it. So intuitionistic logic kind of helps. So this is a picture, an example of the discourse where we have like first set, second set, and an arrow. But in this artistic representation, we have sets like in 2 instances of time, before and after. So we have a big set T, which is like T from before, and T after. And there's a transition from before to after. And there's a subset that defines something that we have there that is not, maybe not the full set. And we have a subset here, and of course the function should map it to a subset here. So what can happen to all possible instances? Look at instance x0, well, instance x. So it's a point x0 here, and it's not in U. And after the transition, it's still not in U. So it's like, it represents something that is totally outside. Point Z represents something that is always inside. And there's one more tricky thing, point Y, which is like half there. It's not there, it wasn't there before, but it's there after. So this is a simple example of non-Boolean logic. But how do we represent this logic? For representation of logic in toposes, there is this object called subobject classifier. It's a special object that is used for producing predicates, for mapping your sets, like running in time, into this thing, and telling like anything that maps here and here. It's like that point A, point Y. Point X maps to that bottom. The fact that bottom is on top is kind of counterintuitive, but and this is the truth, so it's top, but well, it's here. Well, like, you know, we are programmers, right? In our trees, roots are on top. So same thing. Yeah?
Would that be the square in the exponent? Would that be a set 2?
Oh yeah, of course it should be arrow. Yeah, yeah. It should. No, sorry. Yeah, it should be set 2.
Because it's second dimension 2.
Well, yeah. So it's not just like it's not 1 plus 1.
No.
Yeah. So it's like this.
Yes. Thank you very much.
Yeah, I don't know, like problems with rendering. So in general settings, this is how subobject classifier works. So this is the definition of subobject classifier. Suppose we are not in SES, but in some more sophisticated universe with sophisticated logic. Subobject classifier is an object usually denoted as omega, and with a monomorphism with an inclusion of a terminal object into it. Well, in good categories, a unit is always a mapping from a unit, a point, is always a monomorphism. Well, you can check it. So by the definition of terminal object. So this arrow from 1 to omega is called true. Well, it's a point, right? Like any arrow from a terminal object to another object well, that's a definition of point, an arrow from terminal object to your object. So omega is a subobject classifier. There is a truth. And what's its property? For every object x and subobject x1 of x, see this arrow with this tail. So there is a function, there is an arrow from x to omega such that this picture is a pullback. So if you don't know what's a pullback, it's like x1 is the closest object that such a diagram commutes. So if we go back from the picture, so suppose we have this arrow from x to omega and 1 into omega. x1 would be like the biggest subobject of x, making this thing commute. We cannot make the whole thing commute with object x on top because, well, this thing may not map all the points here into true because this is true. So I'll show you examples. Like just having this definition, we can define equality. So in the inside objects, internal equality. So how can we possibly define it, right? We can go through philosophically. No. Look at diagonal, the one that Runer was drawing just about an hour ago, right? The one that is has a right joint product and left adjoint sigma. So look at diagonal x, if we talk about the points of x. Every point of x maps to a pair xx, right? So equality is the predicate that classifies delta, meaning that only such pairs that come from over there go to truth. Others don't. So on the contrary, if we have a function like this, and if it's equality, if we know that it only takes equal elements to equality, so the pullback would be all those pairs that consist of pairs of the form xx. So that's how it is. It classifies delta, classifies diagonal. So just out of this and this universal property, we're going into logical, logical idea. So here we have diagonal classifier is equality. Can we introduce conjunction? Yeah, conjunction is defined it's from omega cross omega, meaning omega is a subobject classifier. It's an object of logical values, right? So which logical values go to true if both are true? So only if both are true, then the result of conjunction would be true. So that's what it says. True, false will not go there. Well, we didn't define false yet. I'll show you what false is. And so nothing else maps to true through conjunction. So that's the definition of conjunction. So how about false? False is defined like this. False is an arrow from 1 to omega, that is a point in omega, such that it classifies 0, empty. Meaning nothing from here gets into truth. So that's the complement of truth. Meaning if you take a conjunction, the conjunction, well, it kind of takes some diagram chasing. Conjunction of false and true would be false. Conjunction of true with false would be false. Just because we define it, and the result would be always, only 0 would be always classified by that. Disjunction, it takes like more efforts to define disjunction, but basically the idea is truth either on the left or on the right. So this union gives us the result. The union meaning, yeah, where does like union of object come from? Well, this is a synonym for disjoint union, that is just take two, object A, object B, and this is the sum of two objects. Well, if we have those sums, but again, I'm not going in deep into toposes as a category. It's like set theory, but with it's like set category, but with sophisticated logic. And this is a special case. It shows that, well, we can have more than one subobject of one. So first we have true, like this, right? We have false. So if we have false, right, it classifies empty. True, if we have this true, it will classify the same unit, right, the same one. What else? What other subobject do we have in one? As many as there are points in omega. So remember we had that omega like, and so this is truth, this is like question mark, and this is false. So we have, this is omega, right? Which points do we have there? One, always true. Another, always false. And the question mark. So we had those subobjects of omega, right? It's obvious that what's classified by this, this is the full subobject. This classifies empty, as we see on the second picture on the bottom. But what happens here? If we try to map one here and then figure out what is the subobject of unit, and unit in our case consists of singleton set here, singleton set here, and with the obvious mapping, right? This point goes to this point. So what subobjects do we have? The whole thing, empty, and then the thing that has empty on the left and a singleton on the right. So this is half point. Well, of course, if you have two sets, right? So some sets have something on the right, but don't have anything on the left. So these are half points. These parts are classified by half points. And this is an example that there's no Booleanness. Well, I didn't define negation, and there's a reason for that. It's like more sophisticated. So suppose we have three points of time, like yesterday, today, and tomorrow. So similar to the previous case, we have these things. It's like more schematic. So this is the big set. These are good guys, and here, like, they're good already today. These are the guys that will be good tomorrow, but not today. And here we have like 1, 2, 3, 4 levels. These are already good, like satisfy some of constraints we have. This will be good today. This will be good 2 days later, tomorrow, and this will never be good. So we can draw a picture by just adding one more day here. So this is always like this, and well, it's kind of obvious, right? Like one more day, you add one more stage, like when it will become good. So the classifier looks like this. So tomorrow, the last day, we don't have much of a choice, either yes or no. Here we have yes, no, and not today. And here we have like yes, or, yes, no, and like wait 1 day and wait 2 days. So similarly to what we had before, we can define the logic that works like on each component separately, like on a case by case. So now, that was the part that I was talking about last year. So what's new? we will try to see what can we do with this logic if we don't care about like certain parts. Or is there some sublogic that we simplify? Like if we only care about tomorrow, so whatever happened there, we don't care. Like this will be good, these guys will be good because tomorrow they will be good. So basically we'll have Boolean logic, right? True and false. If we care about today only, the picture is like less, how to say? Yeah, so this is like another explanation of this thing. Good, wait till tomorrow and we'll wait till after tomorrow. If we care only about today, so what would be the logic? Today, we'll have like either this point is good, either we are in good area or we are not in good area. Now, what happens to the things outside of our realm? So here, everything that is good today would be good, right? So these things that we don't care if it's good here, if it was good yesterday. As soon as we know that this guy will be good tomorrow, that's okay. Now, no, tomorrow from yesterday point of view. Now, how about tomorrow? We don't care at all. So we don't. Our predicate doesn't run here. So we totally ignore. So anything that happened there is good for us. So that's how our narrowing of logic, like stop caring about the future and doesn't care about like how it behaved yesterday. So we separate a part of the logic and simplify it. So what did we do here? If we had, like, let's go back a little bit. So we had these things, right? So we have this state and this state. 3 states here, 4 states here. And now we're going to simplify it to only care about these things. Yeah?
On the previous slide,
Uh-huh.
wait till tomorrow becomes good. On today.
Yeah, so like tomorrow from this point of view, yeah.
On today.
Uh-huh.
Wait till tomorrow becomes good on the next slide.
Yeah.
No, on the next.
Ah, see why, yeah.
Because everything in tomorrow is.
No, it's not, it doesn't become good. It doesn't, because see, it's not good today. So if we care about today, see, this is a smaller box, right?
You made everything good tomorrow.
Well, tomorrow, but we don't care about tomorrow.
Okay.
So that's the thing. Like if you look at the whole logic, so this is the only logic that we care about, right? And so if you look at the whole like sequence of events, so if this gets good tomorrow, this event is good for us. If this event, like whatever happened there, it's good for us, but because this is the most important. So what happens here? We expand our good subobject. So the operation, well, it's a closure operation. And this is the property of closure operation. Well, it's denoted as tilde. So 3 properties are X is always a subobject of its closure, and double closure is the same as single closure, and one more thing, like logically, closure of intersection is intersection of closures. I don't know, like if Dana Scott explicitly talked about that, but well, it's a little bit different logic, so a different topology. What I'm going to talk about is Grothendieck topology, and he was talking about classical topology. They are related, but we have to know they're different things. So this is an explanation what's going on with the operation. So here's what's, yeah?
I have a question about the closure, the definition of the closure operator. What I know talks about, instead of the third axiom about monotonicity, if X is included in Y, then the closure of X is included.
Yeah, so maybe that may work as well. So basically I pulled it from definition of Grothendieck topologies in toposes. So yeah, maybe that would be enough, what you are saying, that is like monotonicity. Yeah, I have to check. So here's how it is like regarding logic. So now the good things are only here, right? So this is the whole picture of those like elements of components that are considered good in our logic. So why bottom is there? Because we don't care, right? So it's also included. Whether it's good or not, we only care about this. So what happened here? We produced a closure a closure of truth. So we had just one subobject true, 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 and we applied the closure operation that is identity on this component in this moment of time, and take the biggest one, the biggest subobject here that maps to our truth here, and take the biggest one that basically that we can take. So if we go back and take like coming from here to here, getting that closure, it can be done through closure only applying to truth. So this is how it is. Again, like we have x1, subobject of x, just any subobject, and then we apply some kind of closure. For instance, like a closure that only cares about today. So this closure, of course, includes x1, like over there. But we can also look at this big picture and see that this closure can be built from the closure of J, which is a closure of 1. So in this pullback diagram, we can either define closure on each object like in a specific way, or only define it on the classifier on omega, and then the others will be built. We have x1, subobject of x, that is a pullback of this predicate. And we have j, the closure of truth. So we build the closure of x1 in x by just building this pullback. Yeah?
That means x1 good. x1 tilde is good. Is possibly bigger than x1 is good.
Yes. So it should be like not smaller, not smaller.
Yeah, at least as big, yeah?
Yeah. So that's why. And why is it? Because see, 1 is a part of j. So this would be like this would contain x1.
So it's everything that went to good in tomorrow.
Yeah. Today. Well, it depends on which topology. We'll walk through like example of topology on the next slide. Yeah. So such a closure operation on omega is called Grothendieck topology, and having a Grothendieck topology, having a closure operation, is equivalent to having just this object defined, so that it satisfies certain rules. Well, to make sure that it is a closure operation. So having a closure operation, so having a closure of truth defines everything else. So that's, and of course, in what closure operations can we have in sets? In sets, we have in classifier just true and false, right? 2-element classifier. So since closure should contain truth is there, right? So we have only 2 options. Either we include false or not. If you don't include false, so it's the same, like it's a trivial operation, identity. If you include false, we just fold the whole thing into trivial, like trivial topos, trivial logic where false is equal to true. It's not exactly Aristotelian because, well, it's not two-valued, right? But this logic nevertheless exists. It's just degenerate logic. So let's look at more examples. So in this, like today, tomorrow, whatever. So the top row is the logic for today, right? So in the middle, that's what we care about. And this is the result of the closure of truth. So before, yesterday, today, tomorrow. Now, suppose we care only about yesterday and tomorrow, and we don't care about today. Like another logic, where we only care about 2 points, but not today, like we're sleeping 24 hours. So on the left, we care that, well, this is the good thing that we care about, and tomorrow. And today even the things that are not good today but will be good tomorrow, they're included. So this is the picture of the closure, that thing, like truth, and also this one thing that will go to good tomorrow. So that's the closure of truth in this yesterday and tomorrow logic. Now every day, this is like a trivial topology. We don't simplify anything, don't ignore anything. All 3 days are important to us. So, let's look at the last one, never. We don't care about any of them. So anything like truth, false, whatever, it's all the same. So it's degenerate, and we cannot tell truth from false. Yeah, so this is the logic that logicians kind of ignore. Well, it's kind of wrong because, yeah.
So I don't quite follow the graphical notation. So my intuition would be that the yellow, that the good part would always be increasing, or at least not.
I will see. It's not how to say. You could call it increasing, but it's just a map, right? So it's any function. We are talking about sets, right? So 2 elements here, or like 100 elements here, may map into 1 here. So it's increasing in the sense that this may contain not just elements coming from here. This may contain more. So on this, we have like something here, we have something here, and we have this mapping. And some of them are folding together, well, because nobody said it should be a monomorphism injection. It can contain more.
I thought the mapping, so if it maps to, say, 3 elements, then you use 3 colors, and that...
Well, see, wait a second, let's take a look at this.
I thought the mapping is expressed by the colors.
Yeah, I did. Let's go back a little bit. Like here, right? So here we have like those that satisfy some local predicate. Here, why do they have this kind maybe smaller, right? So this, like light yellow, goes inside, but this thing can contain more elements than those coming from there, right?
So that contains the elements from wait till tomorrow and good.
Not only that. See, like here we have like suppose some element like A, right, belongs here, but there's no like nothing here that gets into that A, so it can contain something more. Then it also contains something that belongs here, and several elements from here may map into the same value here. So that size kind of is like not relevant because some of them fold, some of them there may be more elements here than coming from over there. So that's how it is. So, and this picture where we only care about tomorrow. So if we care about tomorrow, only this method, like whether it's true or not. So if we get like look back into today, so this would be good. Like tomorrow they will be good. This, like all these guys are okay as long as tomorrow they will be good, even they were like totally bad 2 days ago. So this is the closure of truth. Like all these guys that are not in false, they're good. So what happens here? Any combination of like yesterday, today, tomorrow, any combination gives us a new topology, and they're all distinct. So we have a good case, right? Now let's look at a more sophisticated picture. Oh, it rendered good. So TLA plus. In TLA plus, we have like sets, objects, events, whatever, like attached to moments of time. So a set, if we are talking about sets, so we have x0, x1, and so on. This sequence of objects with transitions. So what would be a logic? What would be a subobject classifier there? Like this. So we have false, something that never happens. Like if you have a predicate, and if that predicate is never true at no moment in time, so it will map to its identical false, right? So these guys like help to represent the predicate that are always true. And all these things, all these values, it's like there's an infinity over there, give us a value that will be true, like maybe in n steps. So what happens here? So we have true here, but that predicate, like a day before, a moment before, was not true yet. And then here we are good. So like several steps later, we are there. So that's how the whole logic in TLA plus works. So what topologies do we have? Actually, topologies are pretty simple. For every subset of n, like before for 3, right? For every subset of n, we can separate, like select the moments of time where the things are good. Yeah?
But for 3, you had 5.
Well, I draw 5. Actually, we have all 8.
You have all 8.
Yeah. So like the whole combination.
They're all different?
Yeah, absolutely. Yeah. So if we include like all 3 moments, so it will be this identity. If we don't involve anything that's trivial, and there's like all combinations. Yeah.
Are the subobject
I just didn't.
one-to-one correspondence with the subobject?
Well, in this specific case, yes.
Okay.
And there are like constraints on the category for which there is a one-to-one correspondence. For instance, like if you have a partial order with a well-founded partial order, so then yes. Otherwise, like in this case, see, good question, because in TLA plus, in addition to like every subcategory of n, meaning like every actually subset of natural numbers, we can separate those moments at which we are like checking for truth and not care about the others. We have also this double negation topology. What is it? How can it be represented here? Well, it cannot be represented here because we cannot separate moments of time. In temporal logic, it's denoted as diamond quantifier. And what it means, sometime, eventually. So anything that eventually gets true is classified as is included into that closure. It may be like not there, but can we provide a moment of time? No, because we cannot. One thing can be like whatever in 10 steps, and the other whatever, and we cannot produce the thing. So in this specific case, we have a separate topology that is not represented by any subset of n. So it's like a limit. Like you can talk about infinity, but it has no infinity included. So on the other hand, if we had n plus 1, n plus infinity, so we would always say, that double negation is like something that is true in infinity. But if we don't, so it's not well-founded. So I wouldn't say we're out of luck, just the system, the situation is more complicated. So now how about, so far we had partial orders, right? How about if we have loops, like Groundhog Week, like a friend of mine from, I don't know, like he's in Netherlands, and although he came from Chelyabinsk, he still like kind of feels we're like in this loop, like Monday again. So in this specific case, for this specific category, the situation is totally trivial. Why? Because it's a groupoid. This, like if we go there and then back, the whole composition can be only identity. So it's all this loop is identity at each point. And if we have isomorphism, so there are just 2 topologies. So the topology is Boolean. If something is like okay here, so it means it was okay yesterday, right? Why? Because you take a loop and you get there and it's an isomorphism. So this is actually a trivial case. But we can take a smaller monoid and see how things are like more sophisticated. So Groundhog Day, that's an easier case, but we can view it from different points of view. So this is February 2nd, right? Rita's world. Just every day she wakes up, like she has no clue. So it repeats. So the logic is Boolean, right? 2-valued. And the topologies are trivial. Either it's like the whole good sets, or it's, well, degenerate. But we cannot find anything sophisticated there. From fields, well, like, again, like fields' view of things may like be different from how we think he's thinking, but probably like my artistic representation is that he wakes up, oh, not again. So in his view, is we have an identity and we have like a tomorrow, but this is like the same. So the logic here would consist of these three values. Well, again, it's like it's not partial order. So the logic would be something that is true, false, and something that happens tomorrow. So the topologies here are trivial, meaning like, okay, so what comes like always true. Degenerate, well, like we don't care, true or false. And double negation, which is like applied once, so it will be like true tomorrow, and then again. But as a general public, we watch this movie and we know that things are changing, right? So we know the difference between like day 1, day 2, whatever day, and it's an infinity. So what would be the logic there? The logic is true, false, and all these values that tell us like this happens so many days later. So we can describe this like tell, okay, so many days later, Phil learned how to play piano, like save the boy, maybe didn't save the boy, whatever. So what topologies do we have there? We have trivial topology as before, degenerate. Double negation means like eventually whatever happens to Phil. And also n for a topology that goes through after n steps for each n. So we don't have this like subsets of n. If something goes through after n steps, okay, so it's there. So that would be the picture. I don't remember if I have it.
That's a really good example.
Well, yeah, so like it illustrates. So this was an illustration about like general views of things, diagrams in like interpreted as time. Further, I'll go back to database and probably like tell the things that you already know. Not so many people like knew it like maybe 5-10 years ago, but now it seems like everybody knows. And basically the truth is, like in Beam, bases should be immutable. So I'll go there like from scientific point of view. So look at this. This is a schema, data schema from last year. So we have a human, a pet, whatever types are, and a bond. So this is a category, right? It's like not category 2 or 3. It's like this. So what logic do we have? I'll show you the logic in the next. It's kind of obvious, right? So the logic would be, we can have good pet, good human, bad human. And what values, what like combinations can be over there? Bad human, bad pet, bad human, good pet, good human, bad pet, good human, good pet, but bad bond, and good bond. So it's not Boolean, right? We'll have 5 possible positions there. So it describes, the diagram describes, well, we have 3 sets of like local logical values and 2 mappings. So if we have a value like good human, bad pet, so it goes, it maps to good human here, that point, and to bad pet here. And logical operations, as like anywhere in this kind of intuitionistic logic, are defined component-wise, just by those diagrams, as I showed you. So, like if we have good human, bad pet, and then bad human and good pet, and build a conjunction, so you'll have bad human, bad pet. And it will be preserved. So this is the subobject classifier. Again, like the picture is from last year. So that was a diagram, basically in a database, right? If you have a database, so bond, humans, pets, so we are not thinking about like keeping logical values here. But so this is an abstraction, right? So we think about sets with like triples of sets with 2 projections. So that's why suddenly logic kicks in and we would say like top and bottom, they're not exactly pets, but they're just sets that are used for classifying like good pets, bad pets. And the same here. This is Boolean, like we don't have anything further. But over there, we'll have these 5 elements. So true, false, and like pet, which is like good pet, bad human. H, which is good human, bad pet. And HP, like they're good, but no luck. And the parentheses, in parentheses, you see the results of mapping, like here and here. So for this diagram, what topologies can we have? We cannot have, 3, right? So we'll have the same set of 8 topologies because it's a partial order. So here's what we have, like degenerate, we don't care. Trivial, like we care about everything, humans, pets, bonds. We care about bonds, right? So if it's good bond, okay, so we don't care about humans and pets, but basically we'll have only good humans and pets. And so we can care only about pets or humans, or like pets and bonds, and humans don't matter. Yeah?
So you have 8 different topologies?
Yeah.
There are like 8 different logics, kind of, right?
Yeah, sublogic.
Sublogics. So
Yeah.
how do you think about when someone would use the different logics to think about a problem?
Well, it's see, if you have a database diagram, like usually you have a big database, right? And you want to query to do something, you just point like at this table, and you don't care if user table is bad. So that's a typical logic, right? Even if that user table is total mess, we don't care.
But now I start writing propositions in these logics.
Yeah.
And I start using these different topologies, or
Well, so
if I lived in one of these topologies, what would I be able to do or not do, or what?
Well, see, basically, this topology just shows like what we ignore and what we don't ignore. But because you can draw the diagram, you can see that if we take good users, so like in that table, if we ever care about to look into it, so we'll only have like references to users that are good for us. But if the user points to whatever, like maybe phone number, and if we don't care about phone numbers, so we don't care. That's it. Yeah. Yeah.
Would it be fair in this case to think of the topology as a state and domain as its definition, or it's?
I never thought about it.
Okay.
I don't know. I cannot comment, so I don't know.
Thank you.
So what I want to say that if we have a partial order, if we don't have loops, so it can like all the failures could be totally localized. Like we can say we have like a statement, and we can say, yeah, it's bad here, or it's bad here. Well, because it's like there is special logic that like kind of qualifies it. So now this is a popular database schema. Well, I mean, like many years ago, probably 20 years ago, I was like working with the database, and we were trying to introduce something that is totally generic, and totally generic is this. Like thing becomes this, so a reference, right? Object points to another object, or maybe like, and it's impenetrable, right? So how can you trace like when something happened, like in any process? So something broke, and that's it. So that's why, like I was like people told me yesterday, that's why Apache Beam doesn't allow this kind of things. That's why Apache Beam uses only DAG. DAG is directed as acyclic graphs. So, and we just saw that, well, this thing don't give us anything. So in Groundhog, schema, well, it's actually 3, right? Schema 3. So we know that the logic was like this, so we have these arrows, but they're not, we know that their compositions are different, so it's not like we're not losing much. So we can say, after how many iterations we'll have some stuff good or not. We'll have something like eventually that the TLA plus quantifier for eventuality. And we have trivial topology and degenerate topology. But, well, the thing is, tracking failures is also hard. Well, because of these loops.
So the previous one, your becomes was item becomes it becomes, or
Yeah, so if we look at this, so it becomes, it's like, is it an isomorphism? So actually not. So if you look at it seriously, it doesn't even describe the logic of it. So if you do double becomes, right? So what is it?
is it becomes or is it not double? Is
It could be becomes, it could be not, depending on how we look at it. Like if we look at it as Rita.
This is the free monoid on one.
If it's Freemonoid, so like that's the next picture, right? So in the next picture, yeah, we have Freemonoid. So in Freemonoid, we'll have either the either a specific like point like a to the power of n where it happened, or we know that the logic is like eventually, but we don't know when. And in real life schemas, well, I don't think this is the right audience to critique this kind of schemas, because we all know we should not have this kind of schemas. But that's real life schemas, like arrows from person to company, from company to person. And we had a database like a company ago where we had this, like one user can register as a dependent for another user. And that user is also a dependent. It was about health insurance. So a wife has a plan, a husband has a plan, and on one plan this person like is a dependent, but it's not about the feature of plans. It was like considered as a feature of user, of humans. So okay, so and we have loops like so. Can we go forever? Yeah. So UI was just like crashing on those loops, but now we're like in this place. We know well this won't work anyway. So it's not the right place to talk about how harmful it is to have those bad schemas. But as you saw, actually these things are not that bad. So I say no way to track failures. I have to erase it. We can find a moment, but not always, because there is also this eventually. So that's it. Thank you. Questions? Links. There should be also a link to Dana Scott's talk, because he kind of explained the thing like closure operation, and because he was talking about like finitary, if not finite, operations. So it kind of gives an idea why these things are doable, like why this logic can be built, and say why free monads can be built. But that's a different story. Yeah.
Why don't you like the schemas that are the graphs?
Well, because it produces a logic in which we cannot, like, how to say, we cannot trace like failures. So your predicate, like imagine you have like day after day you are updating the values, right? So your predicate will not tell you when it happened, what exactly happened. But if you have like a queue of events, right? So you keep everything there. So it's a transition like in TLA. So you can always find, and maybe like you care about like the last week, but you don't care about like I don't know, last century, right?